Hello everyone. Okay, so in this video I'm going to discuss about error bounds that we encounter in approximate integration method. Now this is one of those lessons that students struggle with, and I will try to explain in this video why we need error bounds, what are they exactly, how are we going to use them, and what is their real meaning. So if we learn that, hopefully we can understand the questions and the lesson better if we understand the meaning, the real meaning of error bounds. Okay, all right, let's start. Now, approximate integration method is an estimation method. What you do basically is that you estimate this integral, right? So once you do that, you will definitely create an error, right? Either you will overestimate or underestimate the actual integral value, right? So how do you calculate the error? Well, to calculate the error, what you do is you take the approximated value and you take the actual value of the integral and you subtract them, right? Then you get the error. But think about this. In real life cases, in real life scenario, you don't know the actual value of the integral, right? I mean, that is why we use approximate integration method, because most of the integrals you cannot solve them using regular integration techniques. That is why you use approximate integration method. If you know the actual value of the integral, then you don't need to use approximate integration methods, right? So to find the error, you don't know the actual value. So actually you don't have a way to find the error as well. So what error bounds does is that it gives you an error estimation. Okay, so it will give you the worst case scenario, the worst error that you can get from the method. So you are using different methods, midpoint method, trapezoid method, or Simpson's rule. So the error based on an error estimation based on the method can be obtained using error bounds. So think about this example. Let's say you have a car, you want to solve this car, and you bought this car a few years ago for like $6,000. Okay, now you want to solve it, not solve it, sell it. Okay, all right. Now when you want to sell it, let's say you want to sell it, you advertise it for $4,000. But you know, people are going to bargain, people are going to try to negotiate with you. So you decide, okay, so the lowest I will go will be $3,000. Okay, if they bargain. Okay, right. Now, to make your financial plans, you know the worst case scenario, the worst loss that you can get out of this scenario is 3,000, right? If they bargain and if you manage to sell it to 3,000, then that's the worst case scenario. But actually, when you sell it, you don't know, right? You might be able to sell it to 3,500, or maybe able to sell it to 4,000, but who knows until you sell it, right? But you know, from this situation, the worst you can get is a loss of $3,000, assuming you are very well capable of selling the car, right? So something like that. So error bound will give you something like that, the worst case scenario. All right, so let's go to the inequality. Well, this first inequality is for the midpoint rule. So there will be an error bound formula for each method, different error bound formula for each method, right? This is the error bound formula for the midpoint method. Now the left hand side is actually the error. So why do we have absolute values? Well, we say that the error is positive. It could be overestimate or underestimate, right? We don't know. So let's say the error is positive, okay? And the right hand side will give you the worst case scenario, the worst error. Okay, it will say like, think for like the right hand side, let's say like 0.01. Okay, so for midpoint method, 0.01 means when you use the midpoint method to approximate a certain integral, okay, the worst error that you can get is 0.01. Your actual error is guaranteed to be less than 0.01. Okay, so that's what the error bound says. The right hand side of the error bound says. Okay, let's look at these terms. Now these terms, if you look at b and a, most of these terms are obvious. Okay, so b and a are the upper and lower limit of the integral, so that will be given to you. You just need to look at the integral and figure them out. That's easy. N is the number of rectangles or number of subintervals, so that should be given pretty easy. Okay, so n, b, a, they are very easy. Here we have capital K. Now what is capital K? That's the part that most of the students struggle. The meaning of the capital K for midpoint rule, that it is the bound of the absolute value of the second derivative. Okay, where the x values are between the lower limit of the integral and the upper limit of the integral. Now what do I mean here? So here's what you do. When you are given a problem to approximate, given an integral to approximate, you look at the function, you take its second derivative. Okay, and you take the absolute value of that second derivative and try to bound it by a certain value. Okay, and that value will be k, and you have to remember your x values cannot be anything. It should be between the x values a and b. Now to understand this, we have to do several examples. Okay, so that's what I'm going to do starting from next video. Okay, this k, finding capital K, depends on the function that they are given to you. Okay, it could be an increasing function, decreasing function, oscillating function. So it's always, finding capital K always depends on the type of the function. Okay, so there's no clear one way to figure out k. Okay, but I will go through every type of example function and I will show you how do you find k depending on the function that's given to you. Okay, so in the next video, let's start with a very simple example for midpoint rule. Okay, and then let's use that example to figure out the error bound. So that's what I'm going to do in the next video. Okay, so overall the idea of this error bound lesson is that you're finding the worst case scenario, the worst error out of your method. Okay, understand that idea. It's like the maximum error that you can get, but the actual error should be smaller than the worst case scenario. So that's why you have this inequality. The actual error should be less than the worst case scenario, right? That's the truth, right? So you will get an upper bound for the error. You get an error estimation. So what happens here is that you also estimate the error, not only the integral value, also you approximate the error, estimate the error also. Okay, all right, so I'll see you in the next video with a simple example, and let's learn how to use the error bound formula. Okay, thank you very much.